Good afternoon to all of you. I am Ramendran Yamman, HOD Department of Physics, Syed College. Here we are assembled here, all over India and maybe over some part of the world, to witness and to participate in a webinar organized by Doctrina 07 of Syed College. Our chief guest today and chief resource person is Dr. Santhosh Mathew, who is a professor, researcher and science writer, and he tries to decode science for those with an aversion to it. He has written 3 books and has written several articles. His research interests include developments in modern physics, mathematics and cosmology. At present, he is working as Associate Professor, Regis College, Boston, USA. I welcome you, sir, to this webinar. I also welcome our beloved principal, who is with us today, and he is Lieutenant Dr. Muhammad Ashraf Warbuli. We welcome you, sir, to this function. Also, I welcome Dr. Abdul Salam, coordinator of Doctrina 07, and Dr. T.P. Nafisa Baby, coordinator of IQAC. Dr. Jafar MP is the department coordinator. I welcome all of you. In addition, I welcome all the participants who are in different parts of India. Once again, I welcome you all. Thank you.
So my plan is probably I will speak for 40 minutes or so, as I was told, and then I can open it for some sort of conversation, like discussion or questions. I think the best way to do that probably is you can send the questions through the chat box or something, and then I will try to address those questions. So the topic that I choose, initially I was a little hesitant because I was not sure what exactly, with a wide variety of audience there, that you are exactly looking for. But then I thought, because some of you are faculty members, then of course there are students there. So I thought something that I should speak about is more about physics education and how we have to change the traditional way of teaching. Especially, I had my entire school in India, so I have that kind of experience. So, but I thought that it's time, whether we are in India or in US, that we need to get out of that typical traditional model, and it's little, it'll be beneficial for everyone, for the faculty, for the student, and overall for the higher education. So here is the overview of my talk today. So I want to briefly go over some of the goals and then some of the factors affecting physics education, and then I can share some of the possible solutions with a warning that whatever I share is based on my experience, and it may not be a universal solution for everyone, but you can always take it from there and customize to the needs of your institution. In order to accomplish this particular topic, what I choose to do is I decided to take 3 well-known equations from probably most of you are familiar with. In fact, it was part of my last book also. So I took 3 examples, and I will have a discussion on those 3 equations in coming minutes. And then at the end, we can have a discussion or conclusion, and I can address your questions. So I just put it as a, overall what you would accomplish by doing this particular webinar. Primary goal is to create some interest for students and faculty about some of the well-known, physics ideas, which probably you all know already, but I want to take it in a different context. Similarly, with my experience in Indian universities, when I was a graduate and postgraduate student, a lot of time we learned physics equations in a very dry and, quite often very boring manner. I have to admit that. And, a lot of time, as you all experience, our generation, we prepare that. Of course, we prepare that for the test scoring skills. But we kind of leave a lot of meaning or in-depth discussion about some of the equations that we study in physics. So, I want to use this opportunity to bring that discussion back into the array and, create some interest. Also, one of the things that's happening in higher education now is, I don't think we can live lonely life now, in the sense you cannot have this segmented departments or subject fields. We go to get out and collaborate with other people. Now that doesn't mean we have to be all the time doing it, but there are opportunities and avenues where physics department can collaborate with other departments, other institutions. And if you look globally now, this is the key. Overall, the enrollment in physics education for masters and undergraduate both, they are on a lower trend now. So the way to kind of address this issue is probably we reach out to a larger audience. We have to reach out to different disciplines and then create something new. For you guys to get an idea about this, I put this statistical data from the American Physical Society, one of the largest and well-known professional organization who collect data from physics graduates. I want to briefly touch upon what they are talking about. If you look at this graph, this is the data from 1967. The red line is the physics graduates, bachelor's degree, and the blue is the STEM, in the sense science, technology, engineering, mathematics, everything other than physics. So if you look at 1967, you can see that there were more physics graduates than all the STEM fields combined. Now look at by 2017, you would see there is a marked difference between the number of graduates in physics and other fields. Now, part of that I fully understand, because our world has changed from 1967 to 2017 or 20 completely. We are now in a world of technology and big data. So obviously people are going to choose the majors that will give them more job opportunities or earning capacity, those kind of stuff. So that part I fully understand, but I still believe physics is one of the subjects that even if you take it in a bachelor's degree, there is a lot of avenues, a lot of opportunities for people to diversify, in the sense they can go to many other fields, not only in STEM, even in non-STEM fields. I have seen some of the physicists working in Wall Street, and these kind of opportunities are plenty out there. So I thought this graph is quite interesting, and the natural evolution of our society is being reflected in this graph, in the sense 1967 was a totally different picture, how people would choose a major compared to what you are to do in 2020. That part is fine, but I still thought it's an eye-opening, data for everybody to look at it. Then I have also created another for, especially for students. And now I have to admit, this is the data mostly taken from some of the US organizations, but professional physics organizations, but they do collect the data from non-US citizens. In the sense, the city that I live in, Boston, we have at least 20,000 foreign students in a particular year here. Because of the pandemic now, things are a little disturbed here, but normally we have about 20,000 foreign students living in our state here. And we host some of the big universities like Harvard, MIT, Boston University. And the college I work is an average university, but in a few minutes, I'm going to share with you, even when you work in a smaller place or in an average university, the collaboration with other institutions can take you to a different level that we can't even imagine. So that is another thing that would be coming up. Again, before I get into my actual talk, I want to show you one more thing, a graph. Again, I collected from these professional organization websites, which I am part of that, American Institute of Physics. So if you look at the skills or the knowledge that is employers are looking in this economy is, you can see a lot of them listed there. You don't need to go through all of them, but what I found, I want to highlight a couple of them here. One is, being with my experience in India, when I was a physics graduate, there was not enough attention given to things like writing, technical writing, or even normal writing, or even teamwork. Other than what we do in the physics lab, I don't think there was much opportunity for teamwork there. And then obviously one thing was missing that I found very interesting here when I came in about 18 years ago, was the internship or applied research or independent study, those kind of stuff that was really missing when I was in India. I know a lot of things have changed. You have innovated hugely, but I still believe these are the topics that we can always bring to our table in order for a discussion, right? Now, if you ask me why that, remember that graph that I was mentioning, the lower enrollment in physics education, some of the things that I found, again, I'm not putting these ideas as a universally acceptable fact or something. It's mostly my own experience and my own thinking. Obviously, it is a little subjective, but you can take it from whatever discussion we have. You can take for your own convenience. Of course, one of the things that we all know is poor preparation in math and science, which is true. Obviously, there is a perceived difficulty in subject like physics across the spectrum. A lot of people think it's quite difficult. And then there is a poor outlook, which means when you have a physics degree, people often think, what am I going to earn? What am I going to get in? Where is the job market for this? So that is another issue, which I agree, especially with data and computer science ruling the world. People normally would look into those kind of field as a quick way of getting employed. But what I found very interesting is among the students, one of the things that is missing is the motivation. All right. Now, the motivation is not something that you can, just, kind of impose on somebody. It has to come from you, correct? So in general, what is happening is, the physics education has barely came out of its that traditional mold. So usually when I teach physics, I know probably you all are able to recognize this figure that you are looking at now. That is Richard Feynman, one of the very well-known physicists who died back in 1980s, late 80s. He was part of the Manhattan Project. He was a professor at Caltech, California Institute of Technology. But above all, he was a huge source of motivation for a new generation of physics graduates. Because he used to speak, I'm sure you all heard about this famous, the Feynman lectures on physics. It is still taught in, even though it is like almost 30, 40 years old now, I guess. I use it still in my physics classes. It's freely available on the website Caltech division. You can just put a Google search, or I can share that information with anybody. I'm sure a lot of you heard about it. It's quite old in the sense it's from 1970s and 80s, but it's very interesting to look at these kind of stuff and create some sort of, I'm not saying this is primarily meant for an information, because information is free now. You can have all the textbook free. I can give you all that information. Probably you all using that free textbooks. Anything that you need, it's over there on the internet. So it is not the question of information. It is how you shape a student's attitude towards the physics, right? So that's how I found Richard Feynman as an interesting character. And in one of the BBC interviews, he mentioned, he was talking about the Bohr atom model, that equation, and but instead of going in a traditional fashion of deriving Bohr equation, what he was saying is, look at the statement that he made. He was saying, look at that little neat equation. It tells me all the ways an electron can make itself comfortable in and around an atom. And there is poetry to that, because there is questions being answered, how, for example, how the rocks are hard, or why the grass is green. So what he was trying to do here is taking an equation, giving that equation some life, instead of putting it as a, the normal way of teaching physics. We all are part of that. We take it from somewhere, fill the board with a few steps of mathematical derivation, and will present to the student as a final product. I think that is very, in fact, that kind of skill is required. But in addition to that, we also need to bring some sort of enthusiasm, some sort of life and dynamism for these kind of equations. So that is primarily my goal. So with that in mind, last year, my third book came out, actually a year ago. So I used 10 equations from physics to explain the mysteries of modern astrophysics. So some of the equations are sprinkled here, that probably you can see that, Boltzmann's, entropy, or those kind of equations are here. But my whole point was, take these equations, apply them in different fields. It's nothing new. It has been done for generations by physicists. But at some point, we tend to live in an island. We don't want to reach out to other disciplines. We don't want to apply physics to something else. We still go with that old traditional mold of textbook teaching. I think it is high time that we need to put a stop to that, because otherwise we are going to lose the students. The students, after graduating, they have to have an idea, not only just about the mathematical derivation of physics, that I admit, that is a skill that you need to have, but beyond that, they need to gain certain skills. Now, one more experience I will share with you when I was writing this book, and which you can see here. As I mentioned, I teach and research in a very average university with 4,000 students here, which is in US standards considered as a average or small university, because a lot of them have like a 10 or 20,000 students and some of the world's largest research institutions. But one of the goals for this webinar is also I want to encourage everybody to go collaborate with other institutions. That is our future. We cannot live within our own departments. That age is gone. That's my point. So as an example, I am putting on the screen. This is the review by one of the world's renowned physicists, astrophysicist, Avi Loeb, who is the chair of the astronomy department at Harvard University, and also he is the founding director of Black Hole Initiative. He wrote this for my book. This was a review that he gave to me. I mean, I'm showing it as an example how, as a faculty from an average university, we did some of the outreach to reach out and collaborate and work with the big universities. And the benefits, that's not just for my book, it is for my students, it's for my institution, and it is for the physics. So my primary theme is this, the collaboration, creating courses in interdisciplinary areas, multidisciplinary education. Those are, in my experience, going to rule the world, right? So it wouldn't matter whether you are in a small college or a big university. You can always, especially in this digital age, there is no limit how much collaboration we can have. And I have to admit that during one of my sabbatical period, I had the opportunity to work with the Harvard University Astrophysics department. I mean, if you ask me, I was not doing any high-end physics research. Of course, it wasn't, but I was able to collaborate with them, bring back something to my students and something to my institution. So that is one of the primary themes I think we should keep in mind. With this in mind, I'm going to show you in next few minutes 3 equations that I choose to present. Again, I wouldn't be going through the mathematical background or anything of that equations because of the audience. We can have more like a qualitative discussion. So the first one I choose, it is in fact the first chapter of my book. I named this equation, which you are going to see in a minute, the equation that gave us a digital life. Now, we all are enjoying the digital life now. I mean, without that, I wouldn't be communicating with you, or I wouldn't be seeing you at this point. So people are, it's easy to forget when these things become so common and popular, we tend to forget how this came into being, how what we call the digital world now, everyone sending, videos, photos, sharing information, how this came into being. I mean, I put a quote from John Wheeler, one of the American physicists who, in fact, coined the term black hole, the very popular name black hole. It was originally not called black hole, it was called the singularity of space-time, something that sort, but he is the person who put that black hole name into the picture. But what my equation that I'm going to show you in 1 minute is the equation I believe opened the entire world of digital life. So, in fact, as I mentioned a minute ago, it's very easy for if you ask a kid from new generation, they would think that there was always internet or there was this kind of communication. But we all know, a lot of us know that it is not true. These are relatively new things, and we are kind of in an evolving fashion. We are just adjusting with that. But if you think all these, how this what is the breakthrough? What is the starting point of all these communication? If you ask me as a physicist, my answer would be this particular equation. And I want everybody to take a look at this equation. It is not like I mentioned, we are not going into the details of the mathematical depth of that, but being in physics, probably you all understand the signs and symbols here. So the equation reads H, which is what they call information entropy or Shannon entropy, because that is the whole point here. This equation was first derived by Claude Shannon while he was working at the Bell Systems Technical Lab. And the paper was a mathematical, theory for communication. That paper is a well-known paper, and this is the first equation that he put it there. Now, I thought I could teach probably this to my students in discrete math or computer science or even in physics. I can go simply by writing this equation deriving from the original paper of Shannon. I can show them how this is, or I can pick up some of the probability here and show them the entropy calculation, but that is the traditional way of doing it. There is nothing new about it. And I don't think people are going to pay a lot of attention to that, because that is a skill, I admit it, but that is already out there. This equation is well derived. With physics and math background, we all can understand how Shannon reached this equation, which was published in 1948. But then I thought, why don't we give some life to this equation? That way, students would enjoy, the faculty can take it to another level. We can create some collaboration with various departments, which I'm going to show in a few minutes, how that can be achieved. So what I did is, I did a thorough research on Shannon, who lived most of his life in the same state where I am. And he was also part of MIT, the Massachusetts Institute of Technology. And he was a professor there for some time. But what I found so much interesting was Shannon was buried in a cemetery probably about 20 miles from where I live. So this is the gravestone that you are looking at, the Shannon's gravestone. So this is a picture that I took it when I visited that place, of course, with the permission from his family members to use it in my book. So I think if any of you missed this, you have to connect it. This is the equation I am referring to, which is often called Shannon's entropy equation or information equation. And as you might know, this is the one that created the entire idea of how information can be shared in the form of bits. Now the term bits is nothing new. Just imagine back in 1948, somebody is saying, you can take information, put them in random bits, and you can share with another place or another person. That is a breakthrough. Now, we can think about all the technology that came up after that, right? You have now, who is going to think about bits now? We are transmitting data probably in terabytes or gigabytes. Nobody going to care about that, right? But in 1940s or 1948, when this whole idea came in, that is what makes me how physics can work in a very deep and subtle way to drive what you call the technology or what you call the modern world. That is why especially I chose this equation. Now, as I mentioned, I wanted to reach out my students to give them a different way of thinking, looking at this equation, give a little more perspective on what it is, why it is important. So give some life to that equation. So not only that I found Shannon's gravestone, with, you can see his name here, Shannon Claude Elwood. He died in 2001. On the other side of this gravestone, you can see that equation is etched there. Take a look at it. I found it, it's not the first time it is done. You know, the very well-known Schrodinger equation is also done similar way in a cemetery in Austria. But I found it very interesting because this was something, say, like 15 miles from my institution. So I thought this is a, you know, great opportunity for me and my students take this particular idea, in the sense not only the derivation and learning about the equation that we could do in the class, but then take my students on a field trip to this particular place. Now, what is the benefit of that? That is the whole point about the changing their perspective or creating some motivation. Now, I had some of the, you know, students who is taking physics. They are not going to be physics majors. I know that for very well. I don't think I have to, you know, overpressure them with all the equations 24 hours. I'm not going to do that. So I wanted to give them some sort of, create some enthusiasm also learning. So we took our students along with some other departments. I tell you in a minute why I chose to do that too, to this graveyard, which is, like I mentioned, very close to my institution. And the students, I can imagine, they found it so interesting. They did a lot of research their own about Shannon and the original paper. Imagine if I did that in a traditional classroom setup, probably they would do a minimum amount of work, what is required, and then get it done. But with this kind of an opportunity, they went their own way. They became independent, which I call an independent research. And also, we were able to create some sort of interdisciplinary collaboration, because I had some of the students from journalism department came along with their faculty members to visit this place, because for them, this was an amazing story, a science story, to put it out there. Even though it was there in some records, it was not quite visible as it is. So the journalism students came with us. Of course, they don't need to understand the formula, but they took a very good reading about the history and science or the philosophy of this equation, and they were able to generate their own outcome. So I achieved two things in brief. One is created some enthusiasm for my physics students to address or learn about an equation. That is one thing. Secondly, I was able to generate a collaboration with another department or departments, and bring them also into the field of science, exposing them to science, because science writing is also a huge and a growing or evolving field in many parts of the world, and I'm sure that is true even in India too. So that is my first equation that I choose to present to you. The second one is, again, it is a very well-known equation. But in my book, I call this equation as the equation that stores eternity. So you can see from the title itself, it can bring some, enthusiasm or some thoughts about even the philosophical world of physics, because you are talking about eternity. That is a concept that is being well discussed in, say, religion or philosophy. So I thought this equation will be a learning moment for many people to combine, say, things like philosophy or mythology or a little bit religious studies. So in other words, you could attract non-science majors also into this kind of business. You can create a course for non-science majors with fundamental ideas from physics. Probably you can co-teach or team teach with another department, other faculty. And then you can create avenues for students to do independent study or research. So I'm sure probably you all will by now probably recognize which equation I am talking about. It's a very simple equation which is being taught in my undergraduate BSc classes back in India. You can all see here. It's the basic equation for entropy. So you will say, okay, change in entropy is Q over T. Q is the heat content of the system, and T is the temperature. In physics class, we will say, okay, temperature in Kelvin scale. That's fine. Now, normally, discussion about the entropy stops there because there is nothing much more to add. Now you jump into numerical problems based on this, which is not very hard to do. But then there is much more to that. Based on this equation, that itself is immense. I can see like thousands of papers that is being written about the idea of entropy. Now, the original idea of entropy was developed in the study of thermodynamics or heat engines, and probably you all know that back in 19th century. And the equation is so simple. But then I thought how we can incorporate this equation in a way that the students will be able to enjoy a little more about it. That is why the name that I put here, the equation that stole eternity, because this is one equation telling, probably those who are in physics, you all know that this is the one equation saying that for a system which is isolated, the entropy is going to increase, and eventually the universe will have an end. That is a very big idea in cosmology based on second law of thermodynamics. But this is the idea, they take it there. All right. So I thought, I have a lot of biology students, and they were, some of them were in environmental studies. So I said, okay, let me research a little more into this, more than what you see in the textbook. You can find it wouldn't take that, it's not like a huge task that we have to undertake. It's very easy to connect the dots. It's very easy to connect across the disciplines. So look at this, one of the iconic pictures about the global warming. It is the Arctic ice is melting. Now, you can find, I have taken this picture from the Geological Survey website. Now, you can take it, you can show the students the paper about it and how the idea of entropy is being used in this particular scenario. So that was so useful for my students who were doing environmental science. They could never thought of putting a typical physics equation into their way of thinking. So basically, I was providing an opportunity for them to apply one of the physics ideas, one of the very well-known physics equation, into something that you see around, something that is a very pressing, very contemporary issue, which is global warming. So I'm saying we all are able to think and connect the way. Nobody needs to do exactly the same as someone else. There is always opportunity. So this will enable students to take physics equation into one more field, which is environmental science in this case. Now, if you have anybody interested in sociology or philosophical, social, those kind of information, you will be surprised. There is even a term called social entropy and the second law of thermodynamics. Who thought a pure physics idea that was originally generated for the study of thermodynamics or heat engines that can be applied in social systems? In fact, some of the well-known social scientists, for example, Steven Pinker, he is one of the well-known cognitive psychologist at Harvard. He used the entropy idea from physics in order to generate a lot of discussion and papers, and of course some of the outcomes are very well accepted in the academia. So he used the very same idea, and in fact this slide I copied his own lines. This is what Steven Pinker, you can Google about him, you will find he is one of the very well-known living psychologist. What he did is took the basic, one of the fundamental ideas of physics to apply to his field. So when I share this story with my students in humanities, they found it quite interesting, because now they can see a connection. They can go, physics is not in an island, you can connect with, you can go. So you are seeing the examples. We can link to biology. We can, of course, connect mathematics, and astronomy is anyway connected to physics. But some of the physics ideas can be taken to subjects that we never thought it is possible, but it is. That is my basic point about this slide. And then, if anybody in the field of biology, I don't need to tell them, there are thousands of well-researched papers and studies about evolution and the second law of thermodynamics. That is a very well-known fact. In fact, some of the biologists, they even use the second law of thermodynamics in order to analyze how the process of aging working, not only in humans, even in animals, the aging works. Because in one sense, the second law of thermodynamics, that is based on the entropy idea, it says there is no going back. The time, arrow of time cannot go back. That is their point. So basically, a simple organism then evolving into a complex one, and the organism itself is going to degrade over a period of time. So that entire process of evolution can be linked to second law of thermodynamics. I mean, I don't want to pay much attention to this focus at this point, because it's mostly about the physics, and I want to respect that time. So anybody interested in biology, environmental science, there is plenty of materials in physics that they can take it from there. So what is the point I'm trying to make with these two equations? My point is, as physicists, faculty, institution, and students, we can create interdisciplinary courses. It is not just the course, even though I put it course here. I mean, interdisciplinary studies. Now, I don't know how much of that is given that kind of attention in India now, but here it has become a survival for many of us in average universities, because we lost physics major, I have to admit, a few years ago, because physics major in US is now residing in some of the big universities. Average universities are unable to run a physics major because we don't get enough students, because a lot of them are doing professional courses and getting, which is the same trend, I believe, back in India too, right? But this is one solution, in my view, creating interdisciplinary education based on physics, which means you are bringing, and in both of my equations, I have shown examples how I was able to engage students from English and journalism, computer science and mathematics. And also in the last slide, I spoke about how I was able to connect with the students in environmental science, biology, or even in psychology. So all these examples are showing how much more we can do with the basic physics. Now, what is the benefit of this? A lot of courses that is being taken as elective in US universities are normally, there is a list of electives, like I'm sure it is same way there back in Europe institution too, and the students choose it. So if we need to create new courses, it should be innovative. It should be, students should be able to enjoy regardless of their discipline. You cannot always look for only physics students. Now, when you create these kind of courses, the cost is nothing. You can always find, for example, I use something called Open Educational Resources, OER. Probably you all are aware. And I hope you all should be, the students and faculty. You don't really need to buy the textbooks now. The free books, free information, it is out there. For example, I can show you the one I use in my classes. This is from the Rice University in Texas. I worked with them for creating some of the free textbooks so that we don't need to pay. I mean, it is a screenshot. I can share that information for those who are interested. But you can see a lot of free. Look at here. They tell here it is peer reviewed, openly licensed, which means it is absolutely free. And you can customize it. You can take it. You can use it for your own needs. So my point is, let's take the physics ideas or classes, make it in a way that it can reach out to other students, not only the physics majors. And who knows, some of them might be interested in doing a physics major after seeing that. Now, one of the challenges when we create a new course is how do you assess this, especially with online environment. But there are hundreds of tools. Again, it is available freely for you. For this, for example, this screenshot, I have it from the Johns Hopkins University website, which is free to use. So you can, they guide you, they tell you some of the tools that we can use for online assessment. So the bottom line is, we don't need to live alone as physicists or faculty or institutions. We can collaborate, we can generate a lot of practical outcomes. For example, after creating this particular interdisciplinary course, and then we were able to do a statistical study, and we were able to publish that work in a journal of science and a journal of STEM. And this impact of OER. OER stands for Open Educational Resources, which is plenty out there. And we assess the students' ability to perform based on the OER materials. So you are seeing one more thing. So the faculty who are interested in publishing papers, this is another opportunity for them to do that too. Now, like this, there are plenty. And of course, you can include your students in this process. That is another thing I found, something that was kind of a shock for me when I came first time here, because the students are involved. I can ask them for the data collection, for the statistical analysis. They don't need to be sitting simply in the classroom and do this. For example, when we did this paper, the statistical analysis was done mostly by our students. And of course, we take a second look at it, but they do learn it by doing something practical, right? They go independent, they go out of their way to help you. Now, I think it's almost 40 minutes, almost. I will touch upon just one more thing about this, and then I will stop, I guess. So one of the other equation I found very interesting was all the physicists know here, that is the Schrodinger equation, the time-dependent wave equation. Again, when I was taught this in my master's class at University College, I never knew a lot of things about this equation. I just memorized it. Honestly, I have to admit, I learned how to derive this equation, and that got me good score in the test and the finals, and I was happy about it. But when I start learning a little more about the Schrodinger equation, I found it so interesting. Schrodinger equation and the Schrodinger himself, he took this idea totally to biology. And he even wrote, a physicist wrote this book called What is Life? This is the Schrodinger book back in 1940s. It's a very, in fact, there is a renewed interest in this book these days, because this is one of the books that created the field of molecular biology. So there is a physicist, we all know Schrodinger, the quantum physicist, he is now creating a new field, not only in physics, in biology, something called molecular biology back in 1940s. So it's a very interesting thing to look at it. Again, this is the graveyard of Schrodinger in Austria. When one of my friends went there to visit it, he sent me this picture. So I just want to show that. And so I'm saying, like, there are multitudes of examples that we can share with these kind of opportunities that enable us to collaborate. Now, finally, I will conclude by saying this. Everyone is thinking, okay, this is the time of big data. What is the equations have to do with? And that is a valid question. But a lot of people now go into data analytics and those kind of courses, which is true, which is good that they can immediately get a job or something. There are hundreds of free data analytical tools available there, and you all hear every day about big data, especially in the time of this pandemic. In Kerala, the data was the biggest news for some time. I've been listening some of the news, and every day I was hearing about data. But some of the discussions that is happening in academia or in a higher education is the data going to replace the equations? I'm not really talking about the physics equations in general. I don't think so. The data is not everything. Data can come with inherent noise. Data can create a lot of unpredictable outcomes, especially that you can see in weather forecasting. You can see that in neuroscience, in epidemiology, in all these fields. It's not the problem with the data. There are plenty of data. In fact, they struggle to keep the data, but how they analyze, that is where the physics come to help, because physicists, by definition, has very analytical thinking. They are very critical thinking. They are quite skilled in those. But probably you and me are not familiar with some of the tools. But my point is, we should bring that also back to our campus, that to our students. That is another area. So all these research, when you incorporate these elements, the data analysis should be another point that you can talk about. And I will normally conclude by saying this. The people who put out this argument, the data going to kill the equations, it is not true. And in order to prove that, I took one of my last argument was this. Okay, so take a look at this. This is the burial site of Stephen Hawking, Westminster Abbey in London. Of course, he was buried. His grave is between Isaac Newton and Charles Darwin. That is intentionally they put it. And you all see on his gravestone, a well-known equation here, which I'm not going to go into the details, but every physicist knows very well what this equation is. This is the equation for the first time gave us a credible information about black holes. Before that, black holes were originally, it was fictional, but then it became purely theoretical. And then we started collecting indirect data. You cannot get direct data from black holes. But then when Steve Hawking came up with this equation, all that changed. Now you don't need the data in order to make some predictions about the evolution of black holes or how they radiate energy. All that can be done with this equation. So that's why they intentionally not only put it on his stone here, and as a respect, he is between Isaac Newton and Charles Darwin in London, in the Westminster Abbey. He died in 2018. You all know that. So what is the point I'm trying to make is here, the data cannot kill the skill of physicists or the equations. But the only thing, we have to reach out, we have to collaborate, we have to create interdisciplinary options and bring a new generation of students and faculty into this process. I think that is I want to respect the time. I think it's almost 45 minutes now. So I finish now, and I open for any questions. I think the best way would be, since there are more than 150 people here, would be you can send me some of your questions by chat or whatever way you want. Thank you once again for this opportunity, and I look forward to answer some of the questions you might have.
Thank you, sir. It was very nice. And most of the participants are writing in the chat box that the presentation was very nice and interesting and informative.
Oh, thank you. Should I look? I can look at if any possible questions.
One question is that, is this online education will spoil the employment of physicists, not related with the topic, actually.
Yeah. I don't think we can adapt. I mean, this is because of the lack of time. I can share with you later, Dr. Nafisa, if you are interested. Probably you have some tools how to run even online labs. I know there is some limitation to that, but it is not going to kill physics or physicists, because we adapt. We have more. Physics revolutionized the whole world. Nobody can deny that fact. You might be living with the big data and technology, but you saw in 3 examples how the field of biology was revolutionized by physics. I forgot to mention that when Watson and Francis Crick, when they discovered the structure of DNA, they were influenced by Schrödinger book, What is Life? So the point I'm trying to make is physics as a fundamental science is going to stay. It is going to revolutionize our field. Only thing, we have some responsibility, in my view. We have to reach out. We have to create new opportunities and avenues. Now, whatever I shared, that is not applicable to everybody. You have to go with your own institutional needs, customize it. So I'm not at all concerned about the physicists going out of business. It's always going to stay there.
Yes, sir. The need depend upon the region, the different places, different situations. I think it is different. The need is different, I think.
Exactly. But the fundamental premise that we are following should be the same. Reach out, create interdisciplinary options, bring new technology, data analysis. Everything can be done. You can involve your students. You can involve, who knows, once they get out with a bachelor's degree in physics, they can go to hundreds of different fields. They don't need to be a teacher alone. They can be anything else, right? So.
Yes, sir.
Any other question?
No questions are coming, only appreciations only in the chat box.
Yeah, I thank everybody, and I hope I didn't make your life hard today evening. I hope I did reasonably well. And of course, I had a lot of, my point is this: you can all communicate, regardless of whether you are in US or India. We should open this channel of communication. We can share a lot of information each other. Especially when these online courses were becoming so common with the pandemic, we were kind of sharing this information with a lot of people, and we are learning a lot from other people. So I want to take this opportunity to say that please keep in touch, keep collaborate, not only just with me, any place, anywhere in the world. We should be opening that avenues and communication open all the time. That's how we expose our students, next generation, to a new world,
Sir, Dr. Avinda asked your contact number, sir. Can I share it?
You can share it, definitely. You can share whoever asks. You have Dr. Nafisa, my email and cell phone number. You can, I mean, as long as we are creating something for physics, I'm happy to be, involved with all of you, So.
Yeah, thank you, sir. Anyhow, it was very interesting, sir. A very new approach towards teaching physics. And
Maybe I will have that personal conversation with you, because I don't know how, probably some of these things you are doing in your own college, I don't know, but there are opportunities I'm interested in learning. Maybe I will talk to you later, so.
Okay, sir. Okay, sir. I think we can finish now.
All right. Thank you, everyone. And thank you so much for your time.
Be there, sir, for 5 minutes, sir. There's a formal vote of thanks.
All right. Sure. Yeah, I will mute myself.
Our Dr. Jafar, a faculty member of our department, deliver the vote of thanks, sir. Please wait there. Okay, sir.
Hi, it is my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of the Department of Physics and all the teams of Doctrina 2020, extend a very hearty vote of thanks to the Honorable Resource Person, Dr. Santhosh Mathew, Associate Professor of Physics, Regis College, United States of America, for delivering a wonderful talk on the topic Equations as a tool to develop an integrated education. The session was very informative and interesting. I would like to express my sincere thanks to our respected principal, Dr. Ashraf Vadapulli sir. Let me express my gratitude to our beloved head of the department, Ramachandran sir. He is going to retire from service today after a long, tireless contribution to the college and society. I would like to express my sincere thanks to IQAC coordinator Dr. Nafisa Baby and the convener of Doctrina 2020 Dr. Abdul Salam sir for organizing this webinar series. Let me express sincere thanks to all the participants from different parts of the country. Thank you all.